All right, thanks everyone for joining for today's TCS Plus talk. My name is Gautam and I'll be the host of today's talk. This is sort of number 2 in our quarantine series of TCS Plus. I'll remind you that if you have any suggestions for talks, we've got a pretty full schedule actually for the next 5 or 6 weeks. In fact, we found a lot of people who are, a little bit impatient or getting restless and want to speak. So we're happy to speak. And so we got a lot coming up, but you can always suggest more on our website. In particular, next week, we're really excited about a more mathematical result by Ramon van Handel. And yeah, but for today's talk, I want to introduce our speaker. Our speaker today is Venkat Guruswami. Venkat is a faculty at CMU. Before CMU, he was a faculty at the University of Washington. Before that, a Miller Fellow at UC Berkeley, and he did his PhD at MIT. Venkat has won more awards than we have time to speak about here. Like just a few of them include being an ACM Fellow, the EATCS Presburger Award, Sloan Fellowship, the ACM Doctoral Dissertation Award, and a host more that we don't have time to say. Venkat is interested, of course, in theoretical computer science. I'm sure we all are, but he's particularly interested in, say, approximation algorithms, hardness of approximation, PCPs, and what we're all here for today is kind of error correcting codes. So without further ado, I'm going to pass it off to Venkat. Venkat, could you please share your slides?
Yep. Right, can everyone see the slide?
Yep.
Okay. Okay, so thanks a lot, Gautam, for the very kind introduction. And it's great to give this talk on TCS Plus. So today I'll be telling you about polar codes, which have a near optimal rate of convergence to Shannon capacity. And this is joint work with Andre Riazano, who's a PhD student at CMU, and Min Ye, who's a faculty member at the Tsinghua Berkeley Shenzhen Institute. Okay, so hopefully no technical difficulties. Let me get to the talk. So in the spirit of the other part of the title, Arıkan meets Shannon. So here is Erdal Arıkan, who's the inventor of polar codes, which we will discuss today, receiving the Shannon Award, which is the highest honor in information theory last year. Okay, so we'll be talking about error correcting codes and communication in the presence of noise. So you have somebody, Alice, who wants to send Bob a symbol X, which is distorted by noise. For this talk, noise is going to be modeled probabilistically. So for every possible input to the channel, which really for this talk will just be 0, 1 bits, you can think of that. There is going to be a probability distribution on possible outputs of the channel, which is given by this W of Y given X. So for every input, you have a probability distribution, and that completely specifies what the channel is. And we'll also be interested in the memoryless setting, which means if you send N symbols on this channel, if you use the channel N times, the channel behavior is independent in each use. So which just means that the conditional probabilities of receiving Y1 through Yn given X1 through Xn is just the product. The conditional probabilities of receiving Yi given Xi. So that's memoryless. And we will be solely interested in the binary input case for this talk, which means the input is just a bit 0, 1. The output can be anything, but it has to be finite. So that's what that's a binary input discrete memoryless channel. And as an example, here is a simple made up channel with 4 channel outputs A, B, C, D. And so the first row is the probability of receiving the various inputs if you send 0. And the second row is the probability of receiving the various outputs A, B, C, D if you send 1. And we'll focus, this is somewhat technical, so not too important, but we will only restrict ourselves to what are called symmetric channels, which means that you can pair up the output symbols in a way where each output symbol is kind of the mirror image with respect to flipping 0 and 1 of the other output symbol. So for example, here you can see that A and B, you've just flipped the probabilities of 0.1, 0.4 when you flip a 0 and 1. Okay, so that's the class of channels we will be interested in. And this is already a very broad class of channels. In particular, so these are called BMS channels, binary memoryless symmetric channels. And 2 quintessential examples of these are the binary symmetric channel and the binary erasure channel. So in the binary symmetric channel, this models bit flips, which happen independently with some probability P. So each bit sent along is flipped by the channel with a probability P. And the binary erasure channel, there are no flips, there are no errors, but the channel can erase the symbol bit, namely replace it by a question mark with some probability delta. Otherwise, the symbol is going to get through accurately. Okay, so I see some things on the chat, so hopefully nothing requires my attention yet. Okay, so all right. So those are two examples of the BMS channel, and particularly the BSC is something very important in coding theory, and that's what we will try to target. Okay, so since you're dealing with channels with noise, if you want to send information reliably, you cannot just send it in the clear. You have to add some redundancy to it. And that's exactly where error correcting codes come in. So you will have a certain message, and which is of k bits, and the error correcting code will encode it into n bits over the channel. And I'll use capital N throughout the talk for the length of the code word. And that goes along the channel for n uses. And then the decoder, based on the channel outputs, is supposed to somehow rectify the error and figure out what the original message was. And we hopefully want m prime to equal m. Okay, and so again, for this talk, we will restrict ourselves to settings where the encoding is just a linear map. So you will take k bits and transform it by a k by n matrix into n bits. And it's those n bits you will send. So the encoding will be linear. And the code itself, the set of possible code words you can send, is simply the row space of this matrix A. Okay. And the dimension of the space is called k, and it sits in n-dimensional space, the block length. And a very important parameter of an error correcting code is its information rate. So for a code like this, the information rate is simply k by n, because you are communicating, hopefully reliably, k bits of information, but you're actually transmitting n bits over the channel. So the rate of communication is k over n. So we would like this to be high so that we are using the channel very effectively. But we are also dealing with a lot of noise, perhaps. So, so there is a fundamental trade-off we have to deal. So coding theory tries to understand this trade-off and then come up with good coding schemes with fast algorithms to operate close to those trade-offs. Okay. So with this backdrop, really one of the fundamental things which governs work in this study is Shannon's seminal theorem from 1948, which said that for every BMS channel, in fact, this holds for every discrete memoryless channel, has a certain quantity called which we now call Shannon capacity, which is just a real number between 0 and 1, I of W, such that the best rate at which you can push information reliably through when you have W as the intervening channel is exactly I of W. So you can get arbitrarily close to I of W, but if you try to push information at a higher rate, then reliable communication becomes impossible. So it's like a sharp threshold for the best rate at which communication is possible. And what I mean by asymptotic rate is that you will use the channel for n times. So you will send n symbols on this channel for large n. And in the limit, the fraction of actual bits or symbols you push through, that k, tends to I of W times n. Okay, so as n grows, you approach that. So that's what Shannon's theorem said. And in fact, you can be a bit more quantitative. It actually says the following: if you want to communicate at rates which are within epsilon of the optimal capacity, then it suffices to take n about 1 over epsilon squared, and and you will succeed in communicating with decoding error probability, which is false off exponential linear. Okay, so that's pretty good because it says that you can keep the rate of communication a fixed constant and achieve smaller and smaller probability of miscommunication, okay, which is a remarkable thing. And unfortunately, one of the drawbacks with this is that Shannon proved this theorem by saying use a random code. And incidentally, this was around the same time, shortly after Erdős's seminal use of the probabilistic method in Ramsey graphs. So this was also around the same time, and it showed that use the power of probabilistic method to show good codes exist. But unfortunately, these codes were not explicitly specified. And if you want to decode these codes, it takes exponential time. So the big challenge which ensued is that can you realize Shannon's dream constructively? Can you give me polynomial time coding schemes with fast algorithms which achieve capacity? Okay, so that's been the challenge. And so just a quick message, what we do in this work, and I'll tell you a little bit about, is we give a constructive, quantitatively strong version of Shannon's theorem. So a bit more specifically, for any BMS channel, we give a deterministic polynomial time construction of that matrix A, which tells you how to encode, and a fast encoding and decoding algorithms. And the rate will converge to capacity at this near optimal speed, which is 1 over square root of the block length. Okay, so I'll elucidate this more as we go along, but if you want already what the punchline of the talk, this is what we do. We realize Shannon's dream in a constructive way. Okay, So there's been a lot of work on capacity achieving codes. In particular, you can first address the question of achieving capacity asymptotically, which means in the limit of large n, does my rate approach I of W? And there are many works which achieve this in some senses. Already dating back in the 1960s, Forney's concatenated codes achieved this. And Gallagher's low density parity check codes had a revival in the mid 90s, and then they were shown to achieve this for the special case of the erasure channel. And this is called tornado codes, and it was a really beautiful work. And around the same time, there also was work on turbo codes, which are not proven to achieve this, but have excellent empirical performance. And then came polar codes, which will be the main chapter of our subject of our talk today, which also achieve this. And a bit after that, there's a variant of LDPC codes, which also achieve capacity in the limit. Okay. But we are not going to be.
Venkat, yeah. Sorry, one question. Yeah. I think someone's curious whether both encoding or decoding in your scheme will be efficient.
Yes. So the encoding will always be efficient in these schemes because the map will be linear. So at worst, it will be quadratic time. And the decoding is more nuanced, but that will also be efficient, right? And in fact, it will be near linear time. Okay. Does that answer the question?
I think so. Yeah.
Okay. I can also keep an eye on the chat, but
don't worry about the chat. I'll monitor it.
Okay, good. All right, good. Okay, so a bit more. So we are not interested just in achieving capacity in the limit. We will be a little bit more precise, and that's what I'll set up here in this slide. So for any BMS channel and any desired gap to capacity, namely you want rate, which is capacity minus epsilon. What we want is the following: we want this encoding matrix A explicitly. And we also want an efficient deterministic procedure, decoding procedure, which takes the channel outputs and outputs what is hopefully the original message. And we want the following property, the correctness property, for any message you send through, which is a k-bit message. When you transform it according to A and then the channel distorts it, the decoder will take that and output M with probability approaching 1. So that's the first thing we want. This is what reliable communication means. And then we want some computational efficiency aspects. And first thing is that this matrix A should be constructed in polynomial time. And then the runtime of the encoder will always be polynomial time because it's just transforming by a matrix. The decoding procedure should also run in polynomial time in n. And the last very important point is that we also want the length of the code itself to not be inordinately big. So we want the length of the code to be polynomial in 1 over epsilon. And Shannon promised you could do this with 1 over epsilon square. But for first blush, let's get it polynomial first. Okay, and really, so what you can really think of is there is a single parameter here, epsilon, which is how close to capacity you're operating at. And we seek complexity, which is complete overall complexity, construction, decoding, length of the code, everything, which is polynomial in 1 over epsilon. All right, so that's the bar we set for this. So this is really summarizes what I just said in the previous slide. And so here, how do these asymptotic constructions fare? Unfortunately, concatenated codes have a decoding complexity which scales exponentially in 1 over epsilon. So it doesn't meet our requirement of polynomial complexity in 1 over epsilon. And the spatially coupled LDPC codes, which was this other capacity achieving family, it's not known that n can be as small as a polynomial in 1 over epsilon. So it's perhaps believed, but it's not proven. On the other hand, polar codes, turns out they exactly meet this challenge. And so far, these are the only known family of codes which have this property of polynomially fast convergence to capacity with polynomial complexity algorithms. Okay, so again, I've just recapped that on the slide. So polar codes, which I'm going to tell you about shortly, achieve this polynomial convergence. And so these were invented by Arıkan in 2008. And he constructed these codes and proved that they approach capacity in the limit. He also gave efficient algorithms for encoding and decoding, in fact, in n log n time. And the miscommunication probability was also later shown to be pretty good. The only thing he did not, which was not done in his work, is he did not say how fast you approach capacity. So the fact that the block length n can be polynomially bounded in how close to capacity you are. And that was done in later works. So one by myself and Patrick Shia, and another by Hassani, Ali Shahi, and Arbanke around the same time. So we basically gave an effective analysis of polar codes, which said that it suffices to take n to be polynomial in 1 over epsilon, and then that gave that met this polynomial convergence to capacity efficiently challenge. Okay, So now that we know that n can be a polynomial in 1 over epsilon, we can ask how small can this polynomial be? Okay, so that's going to be the granularity at which we are asking the question in this talk. So I already said that random linear codes a la Shannon already achieved n as small as 1 over epsilon square. Now there are well-known converse theorems to Shannon's theorem, which says that, these theorems which say that if you operate at rates above capacity, the probability of miscommunication tends to 1. And these basically show that you really need n to be 1 over epsilon square. So basically, if you are interested just in the non-constructive bound, the best block length you can have, if you want to operate within epsilon of capacity, you really have to bunch up about 1 over epsilon square bits and then encode them together and decode them together. So that's the delay, the fundamental delay bound you have to tolerate for reliable communication at rates within epsilon of capacity. Okay, and then as I said, polar codes say that, okay, we can at least get n down to a polynomial in 1 over epsilon. And that has, the exponent has also been optimized, and it's not too bad. It's about 4.7. Okay, but it's not the optimal bound too. And we're going to give this exponent of 1 over epsilon a name. It's called the scaling exponent in the literature. So if you can achieve n about 1 over epsilon to the mu, we're going to call mu the scaling exponent, and the optimal non-constructive value is mu equals 2. So it's natural now what our goal is going to be. The question is, can we achieve this scaling exponent of 2 constructively? And that's basically our main result in a little bit more detail. For any BMS channel, we can achieve rates within epsilon of capacity, and the block length is almost quadratic in 1 over epsilon. And the construction and decoding times are also quadratic. And this result was previously known for the simple case of the binary erasure channel, but we can now do it for any BMS channel. Okay, so so that's the result, and I'll now talk a little bit about what polar codes are and how this result is. Okay. So any questions I can address now?
Let me ask a basic question. Just
Sure.
The random construction. Why is this insufficient for our purposes? You're saying that it's only existential. It's non.
Yes. So the random construction, there are 2 issues. One is that you can pick a matrix at random, and with overwhelming probability it will have this property. But what does that mean? That means that if you get a bit sequence, and if you go to the nearest code word, that will be the most likely and correct code word with overwhelming probability. But the fact that this operation of going to the nearest code word to an arbitrary input sequence can only be done in exponential time, as far as we know.
I see. That makes sense. A question from Klim asking, is the error probability also optimal?
Oh, so error probability also optimal? Unfortunately, no. Great question. I'll come to this later. As I've said here in this part here, the error probability promised here is only polynomially small, and it should be exponentially small, or at least exponent of some power. So yeah, and that trade-off is also understood, but I'll address that later.
Sure. Rohit Chatterjee is asking, can you clarify the dependence on alpha? Apologies if you explain this later.
So I'll come, yeah. So all these constants, order 1, order n log n, they hide constants depending on alpha, and in fact, admittedly bad constants depending on alpha. Okay, so really this should be n to the O alpha of 1, and this should be O alpha n log n. Yeah, great questions. Yeah. That's why I said fix alpha here, so I didn't have to clutter these slides. Any questions? Further questions? All right, so let's go on. So hopefully at least the context and the results are somewhat clear, and I'll clarify it even more as we go on. Okay, so here is the rest of the talk. So we will talk about something called polarizing linear transforms, which are intimately connected to polar codes. And then we will talk about how fast these codes can converge to capacity. And then we will describe our approach to get the optimal rate of convergence and what goes into, brief view of what goes into the analysis. Okay. So again, I'm not assuming any background on polar codes here. So I'm kind of starting from the scratch. So I won't be able to tell you too much about what we do in the end, but I hope to at least give you a sense. Okay, so let's talk about polarization. So this is again something which is very intriguing and connected to capacity achieving codes. So it turns out if you have codes which achieve the capacity of the binary symmetric channel, it implies certain invertible linear transforms called polarizing transforms. So what are those? So suppose you are dealing with the BSC with crossover probability P, or bits get flipped with probability P. So it turns out if you achieve capacity there, you must have an invertible matrix AN with the following property. So I feed it n bits, it gives out n bits, but the n bits I feed it will be n Bernoulli random variables. So n IID bits, each which is 1 with probability p. Should think of this as the noise vector roughly, that's the connection. And then you will transform it by this linear map, and the output you're going to get bits n u1 to ui, u1 through un, and these bits are going to be correlated because you're transforming them in some way. And so what is going to happen in this polarizing transform is that the input, the bits are all independent. In particular, the conditional entropy of any bit given the previous bits. This notation, by the way, is shorthand for all bits between 1 and I minus 1. Okay, all the conditional entropies are equal to the entropies itself. And what happens at the output? Well, first of all, the total by the chain rule, the sum of the conditional entropies remains the same. It's on average h of p. On the other hand, this transformation is such that if you look at these n conditional entropies, basically all of them are going to be either 0 or 1. So that at the input, all entropies are equal, but at the output, the entropies, the conditional entropies are either 0 or 1, almost all. And it turns out such matrices must exist. And so the approach in polar codes is how do we get our hands on a matrix like this? Okay, once again, if you pick a random matrices, it will have this property. The question is how do I construct these explicit? Okay, so this is the property. So basically, it's a linear transformation where the entropies somehow just go to the two boundary values, most of the entropies. And the formal meaning is that for any threshold gamma, if you see which fraction of indices have entropy between, not within gamma of the boundary values, that is going to tend to 0. Okay, and so Arıkan's great insight was to say that, hey, you can use these polarizing matrices, you can reverse this connection. You can actually use such matrices, if you could construct them, to actually get capacity achieving codes. And then he also gave a remarkably explicit construction of these polarizing matrices using some sort of tensor product construction, as I'll show you. Okay. Okay, so for that, let's talk a little bit. I've talked a lot about channel capacity and so on. So let's define what is channel capacity formally. So again, a channel is just a probabilistic way of relating the output to the input. So every channel has something called the entropy, which is the following. It is the conditional entropy of the input given the output when the input is uniformly 0, 1. So it's the average uncertainty in the input given the output. And the capacity of the channel is just 1 minus that. So the larger the entropy, the more noisy the channel is because you have less, you have more uncertainty in the input given the output. And again, that means the capacity is smaller. And in fact, the capacity turns out to be exactly 1 minus the entropy of W. So just examples. So if you take the BSC channel, its capacity is 1 minus H of P, because whatever your output bit is, 0 or 1, the input bit is equal to that with probability 1 minus P and the flip with probability P. So it's like a Bernoulli random variable. So that's exactly the entropy of the channel. So the capacity is 1 minus that. If you take the erasure channel, if your output is either 0 or 1, then you know the input perfectly. So there is no uncertainty. Whereas if the output is a question mark, then you have no idea what the input was. It's equally likely 0 or 1. So the entropy is 1 in that case. So the average entropy is really the probability that you get a question mark, which is delta. So the capacity is 1 minus delta. Okay. So now we will talk about, I talked about polarizing transformation for independent random variables, but now we will talk about independent occurrences of the channel. So what we are going to do for building these polarizing matrices is to start with a very small 2 by 2 transform, and then use it recursively to get a big transform. So what can we do to transform 2 bits? Suppose you have 2 copies of this channel W. So what I'm going to do, so again, what this means is these are IID copies. So the entropy of X1 given Y1 is the same as X2 given Y2 is equal to H of W. And the joint entropy is just the sum of these. They're independent. So it's 2 times H of W. So now let's apply a very simple 2 by 2 transform. In fact, the only non-trivial 2 by 2 transform on bits really, where the first bit U1 is the sum of X1 plus X2. And the second bit is just X2. Okay, that's illustrated here. And so it's just a 2 by 2 transform. And now, since this transformation is invertible, the total entropy of U1 and U2 given Y1, Y2 remains the same. And you can, of course, express that as the chain rule. So it's the entropy of U1 given the outputs and U2 given Y1, Y2 and U1. Okay, so let me just write that down here. So you have this picture now where you take 2 bits, U1, U2, which are random, but instead of feeding them directly into the channel, you transform them thus. and then you feed it into the channel. The sum of these conditional entropies is 2 times h of w. And really what was happening now is that from the perspective of these bits u1 and u2, they are seeing two other channels. They're not quite seeing w itself. The x's were seeing just w, but the u is seeing this channel where you take a random bit, XOR it with u1 and send it on w. And what is u2 seeing? u2 is seeing this channel where you assume that if you look at this conditional entropy expression, you assume you know u1, and then you send both u2 and the XOR of u1 and u2 on 2 independent copies, and you observe the outputs. Okay. So again, for now, you can really think of this as just a syntactic operation. So at the end, what is the channel? It has an input bit and some output bits. So what I've really done here is just view it syntactically. I took 2 copies of w, which are independent, and I produced one channel w minus and one channel w plus. And this is the syntactic description of what those are. Okay. So w minus has input u1, output y1, y2. W plus is input u2, output y1, y2, and u1. Okay. So that's the operation. And again, the sum of the entropies of these channels by this chain rule is 2 times h of w. So I've written that here. On the other hand, we expect that the first channel, w minus, is a bit more noisy, is a worse channel. It's more noisy than w. And the other channel is less noisy and better than w, has lower entropy. So what we have really done here is that we have taken 2 copies of w, which are identical, and produced 2 different channels, w minus, w plus, which have the same average entropy, but one has higher entropy than the other. Okay, and this we have done this by a basic transform, which is called the kernel of the whole process. So we have taken 2 equal entropies, h of w, and split them apart a little bit. H of minus is a little higher, h of w plus is a little lower. Okay, and in fact, these inequalities will be strict unless w is completely random or completely deterministic. So you do create a separation. So now the idea in polarization is going to be to apply this process again and again and again. Okay, and you have to be a bit careful how we exactly do that. So again, we have just done this to produce w minus and w plus. And what you can do is you can do this whole thing on a different copy. And so now you get the first things here are both w minus, and then the next ones are w plus, because you applied this twice. And now what you can do is whenever you have 2 copies of the same channel, you can apply the basic transformation. So you just apply the basic transformation in G2, but to 2 copies of w minus. And you can likewise apply G2 to the 2 copies of w plus as well. Okay, and then you get 4 kinds of channels now. So you have 4 input bits transformed into 4 output bits and sent on the channel. But from the perspective of these bits, they see 4 kinds of channels: minus, 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 plus, plus, minus, and plus, plus. Okay, so and the actual picture is really this. So you have these 4 bits which are transformed according to this process, and then you send the bits on the w. And now you can do the same thing again. You take another copy of the same thing, which is exactly IID here. And then whenever you have 2 things which have the same behavior, so for example, this bit and this bit see the same channel, you can transform them with G2 and so on and so forth. So now you have 8 bits for which you get 8 kinds of channels. Okay, so far it's a purely syntactic operation. And you might be wondering, what does this have to do with coding at all? And we'll come to that. But purely syntactically, I've now described a process which is like viewed as a binary tree. So you start with a channel W. I can produce 2 channels, W minus, W plus. I can apply this minus and plus transform to that channel, and I get minus, 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 plus, and the same and so on. So I can keep doing it. If I do it to 3 levels, I get these 8 kinds of channels. Okay, let me call them W1 through W8. So these are all binary input channels which have somehow been created from copies of W. Okay, so this is the recursive application. So you can really forget this entire transformation, and then that's going to be our invertible transformation AI. So every step we are doing is invertible, so the whole transformation will be invertible. So now we have an invertible transform which transforms 8 bits to 8 output bits. And we also have 8 kinds of channels. The first channel is just U1 as the input and all the YIs at the outputs, because you always observe all the 8 outputs. And again, we abbreviate that as Y18, which denotes all the bits from 1 to 8. And the next channel is U2, which again has the channel outputs. But when you come to U2, you assume you know U1. The way we have created these channels, that's always the case. Every bit, the channel it sees can assume that it knows the previous bits, and so on and so forth. W3 will be this channel, and so on and so forth. Okay, and it's these channels. So again, let me just leave that here for a second. So you have taken 8 copies of W and produced these 8 different kinds of channels. And what Arıkan proved is that if you keep doing this to bigger and bigger depth, if you do it to depth D, you have 2 to the D channels. The average entropy of all these channels will still be the same H of W because every process is invertible. On the other hand, if you count the fraction of channels which have entropy not too close to the boundary, that will tend to 0. And in fact, this not too close can even be something which is like super inverse polynomially close to the boundary.
Hi,
So it
Venkat,
can be
we
really
have
close.
one question from Tsleo
Sure.
asking what is the notation u sub I to the I minus 1?
Okay. So this notation u1 to I minus 1 means all bits from u1 to ui minus 1. So instead of just writing u1, u2 to ui minus 1, I just abbreviated. Thanks. Yeah. So, all right. So somebody circled this.
Don't sweat it.
Okay. All right. Sounds good. Okay. So again, if you want to have a pictorial view of this, you can plot all the entropies of the channel from 0 to 1 on this linear scale. And this pictorial says that most of the entropies are near the boundary.
Sorry, there's one more question from Gopi asking, is it important that W1 through W8 are numbered in order?
Yes, it's going to be important. Yeah. So in fact, the way it is numbered, for the ith bit, the fact that I know the previous bits implies such an order. Yeah. So the ordering is important. Okay. And in fact, by conservation of entropy, once you have polarization, the fraction of bit channels which are going to have entropy close to 1 must be H of W. And all the remaining, which are I of W, 1 minus H of W, will have entropy close to 0. Okay, so this is the picture. Right?
How do you remove the annotation?
Yes, actually, how did that happen actually? So you guys can see this red circle also.
Yeah. Do you want to stop sharing and start sharing again? That might fix it.
Sure.
There we go.
Seems to have done the trick. All right, thanks. Okay, so again, let's plot this. Again, so once you have polarization, the correct fraction of channels will have entropy 0 and 1. So let's plot this for a very simple channel, the binary erasure channel with erasure probability half, whose entropy is also half. Again, it's plotted for n equals 2 to the 8 or 2 to the 10, sorry. So in the start, you have all the 1024 channels have the same entropy, 1/2. After the first step, half of them have entropy 1/4, the other half have entropy 3/4. So their average is half. And then you can keep doing this. Each step, you take a line segment, you split it into half, half, half. One goes up, one goes down. So let's do it one more step. Level 2, level 3, level 4, level 5, level 6, and so on. And you see the polarization happen. So by level 10, almost half of the points are sitting at the top at entropy 1, half of the points are sitting at the bottom at entropy 0. Okay, and that's just an illustration. So all that is good. Okay, what does this have to do with coding? Right? So the idea is once you have the polarization behavior, the idea is simply that you have half of these channels or capacity number of these channels which are actually behaving as if they have no entropy, they are noiseless. So you will just place your information bits there and then send them through, and somehow this process, it will behave as if there is no noise. Okay, what do I mean by that? So formally, let good be those indices where the entropy is very small, gamma, and gamma you should think of as some, say, 1/n square or something very small. And then by the polarization theorem, the fraction of good indices approaches the capacity. So the idea is simply going to be use those indices to hold the information bits. And all the other bits, I'll just freeze to 0. So pictorially, suppose in this 8x8 transform, let's say the good indices are 3, 5, 7, 8. Then I will take my information bits and I'll place them in these locations. And the remaining bits will be frozen to 0. So those will be frozen to 0, and then these 1010, the message bits will just be placed here, and then I'll transform this, and that will be my encode. All right, so why is this a good idea? So when you think of the decoding process, we will decode these bits successively. And that's why this ordering is very important here. For indices which are not good, well, we know that UI should be just 0. For indices which are good, where we need to find out this information bit, so we are going to try to predict UI, give it all the channel outputs, y1 through yn, as well as the previous bits. That's why the ith channel always assumes that you know the previous I minus 1 bits. That's the actual channel you have to worry about.
Venkat, there's a question from Clint.
Yeah.
Do you know which entries have entropy 1 and which has 0?
I'll come to that, yeah. So that's not obvious at all. And in fact, I can at least quickly show that in this picture also. If you look at this picture, you would expect maybe the initial entries have an entropy close to 1 and the later ones are close to 0, but the picture is not quite that simple, even for this very simple channel. Okay, so it's more nuanced, but you can find out which ones are good and bad, and that's necessary for the code. All right. So for the decoding, so these are the channels we have, and now because the channel, this predictor will have an error which is at most the entropy of the channel. So you can predict the ith bit based on the previous bits with error at most gamma. And then if you want to understand what is the probability I make a mistake in any step in this thing, it is just by a union bound, the sum of these entropies, and that is at most n times gamma. Okay, so that's how you can. And if gamma is much less than 1 over n, then we are in good shape.
There's a question from Yuval Filmus asking, the entropy is close to 0 only on average over the values of the frozen bits. Is this a problem?
Okay, excellent question. Very subtle question. Yeah, it's only true for average, but because of linearity, it also holds if you fix those bits to 0.
Okay, there's another comment.
Yeah.
Sorry, there's a comment, I guess, from Andrei Rizanov. It might be a question, but just to confirm, both the encoder and decoder know the set good?
Yes. Yes. Yeah. So the code, so again, okay, so let's talk about, actually all of those things will be addressed here. So if you want to actually get a full-blown honest coding construction, well, first of all, let's talk about achieving capacity. The fraction of good indices approaches 1 minus h of w, so we achieve capacity, at least asymptotically. To construct the code and the encoder and the decoder, we need to find the set good. Okay, so this can be done, and it's not obvious, but it can be done. The encoding is no problem. It's just a linear map, so it's straightforward. The decoding, you have to predict this bit UI given the channel outputs and the previous bits. This is in general difficult for an arbitrary linear transformation, but here because of the recursive structure of the linear transform, you can do it. And in fact, Arıkan showed how we can do the decoding as well as the encoding in n log n time using some FFT-like recursive structure which underlies this construction.
Sorry,
so
there's
that's
one
great.
Question/comment from Arya. Can you not take 10,000 random inputs, look at the empirical distribution of the output, and decide the 0 entropy channels?
Yes, so that's one way to do it. So if you have if you want to predict a randomized way to construct the set good, you can do it by sampling. One issue with that is that you can only estimate those things to polynomial error. So if you want to get exponentially small error probability, you have to use other methods. But for polynomial decoding probability, that will suffice. Yeah, it's great. So people are all on predicting my next move, which is good. Okay, everything is great. The only trouble is that this only achieves capacity in the limit of large n. So if you want to prove polynomial convergence to capacity, near quadratic convergence to capacity, you have to estimate this first step much more carefully. So you have to understand how quickly the good indices approach capacity. Okay, again, that's asymptotic analysis. So if you want to get a scaling exponent of mu, then you really need to prove that the fraction of good indices is at least the capacity minus this inverse polynomial function of n. So 1 over n to the 1 over mu. So that's what you need to get. And this is what was shown in these works in 2013. Okay, so in particular, we showed that it was finite. The parallel work, in fact, said you can achieve mu's at most 6. And that was improved to actually around 3.6 for the BEC and about 4.7 for arbitrary channels. So that's pretty good. But one of these works also showed, unfortunately, that no matter what BMS channel you take, if you use the standard kinds of analyses of polar codes, you're not going to get a value of mu which is less than about 3.57. So this said that polar codes, at least while they're very good in polynomial convergence, they seem to be limited in that they cannot get to quadratic convergence. So that now raises the question, is there a way to get this optimal scaling exponent of 2 using polar codes. Okay, so that's what we're going to address in the last part of the talk. Okay, which is actually the main focus. Okay, so for this, we're going to generalize polar codes. So how might you generalize this basic setup? One thing is we really only focus on binary inputs. We can definitely consider other inputs, but I'm not going to worry about that here. But one other thing you can do is instead of this little 2 by 2 transform, you can actually use bigger L by L transforms. Okay, so what we did was we had this simple transform, 2 by 2 transform, which we recursively applied in a binary tree. Instead, what you can do is that at every step, you can apply a little L by L transform, take L identical copies of a channel and transform it to L kinds of channels, W1 through Wn. And then you apply this process recursively in an L-array tree, and then you will get these channels and you can try to, and everything really goes through. The hope is like, do things get better? So that's going to be what we are interested in. And again, all these results I said so far was for the case for binary codes and this basic Arıkan's 2 by 2 kernel, including the limitation result. So what happens for larger kernels and other alphabets? A couple of years back, so we showed in this work that for any kernel, any L by L matrix and any prime alphabet, it is always the case that the scaling exponent is finite. So this showed that this polynomial convergence phenomena holds universally for all polar codes, which is very encouraging. And now, so then the question is, can you actually leverage this to say that if you make the kernel bigger, mu actually gets better? So that's the question we are interested in. And indeed, this is a very natural question, which is in, and people studied this first in the context of the binary erasure channel. So already at L equals 8, you can beat this lower bound of 3.579. So you can go below that. And if you keep increasing L, so these works of Fazeli, Vardy, and Yao showed that at L equals 64, you can go scaling exponent below 3, but for the binary erasure channel. And soon afterwards, it was also shown that you can, in fact, get scaling exponent to the optimal value for the erasure channel. So this was first shown for large alphabet things by Pfister and Arbanke. And then this beautiful work by Fazeli, Hassani, Mondelli, and Vardy showed that you can actually do this for the binary erasure channel by picking bigger and bigger kernels. Okay, and this work served as a strong inspiration for our work. And we now can show that for any BMS channel, say the binary symmetric channel, by picking bigger and bigger kernels, we get a scaling exponent approaching 2. Okay, and that's our main thing. So I'll flash our main result one final time, and then I'll talk about the ingredients. Okay, so again, the main thing you want to notice here is that the scaling exponent has become very close to 2. So it's almost 1 over root n. The rate is 1 over root n in capacity. And this is obtained by using polar codes with kernel L, which is a big enough constant depending on alpha. And then unfortunately, the constants hidden here all depend on alpha. So the construction time, as well as the encoding decoding time, hides constant depending on alpha. And one more drawback is that the decoding error probability is only inverse polynomial. It's not, say, 2 to the minus root n or something which you would like. Okay.
How bad is the dependence on alpha here? Is it like exponential?
Yeah, so dependence on alpha is bad because the L itself has to be exponential in 1 over alpha. And L sits in the exponent of the construction time and probably in a polynomial way in this time, or maybe even exponential. So it might be doubly exponential in 1 over alpha. So yeah, as stated here, therefore, it is primarily a theoretical result which shows you can realize Shannon's theorem optimally, but clearly there is more work to be done in improving the constants. Any other questions? Okay, so now I'll talk a little bit about our approach, and I've already indicated what we are doing here is that we're going to replace this G2 by some L by L matrix. And again, you should just think of applying this matrix at every step. So you get L different kinds of channels. And every time I should maybe tell you what this thing, when you apply this, the ith channel is simply going to be this. It is UI is the input. The output, you assume you know all the YIs and the previous bits.
Sorry, there's a couple of questions actually. Is there an intuitive reason why the scaling exponent improves with large kernels?
So you will see that in actually the way we prove it will become actually apparent. So you can also think of the kernel itself will be random. So some sort of random coding behavior starts kicking in even at the local level. And we just bootstrap that to get codes at the overall level. So,
okay.
Yes, I think that should become apparent shortly. So, what is the other question?
There's two more. One is L not doubly exponential in 1 over alpha?
L, I think, is singly exponential in 1 over alpha, if I remember right.
Okay, and one more asking, these results inherently all assume SC decoder, i.e. no list version is considered?
Yes, so no list version is considered. If we ever make a mistake in decoding a bit, we have failed. So there is also a list version for those who may not know this, where you maintain some number of possibilities. But from my knowledge, I think those things are not known to, in fact, are known to be not able to improve the scaling exponent or other things. So from a theoretical standpoint, we don't need to consider them. But from a practical point, they are, of course, very interesting. Okay. So let me continue. Okay. So basically, instead of G2, we apply this. So again, think of this syntactically as this transformation of channels. You have L bits, you apply K, you get L output bits, you send them through independent copies of W. So at the outputs, all the bits see the channel W, but at the inputs, these guys see different channels. The ith bit sees a channel which sees all the outputs, but also the previous I minus 1 bits. And the hope is that polarization will happen fast for these kinds of channels. So you apply this process recursively to depth D, so you're going to get L to the D channels at depth D. And how do you show fast polarization? How do you show that a good fraction of channels are good within n to the 1 minus 1 over mu? It suffices to show that the fraction of channels which aren't too close to the boundary is also at most n to the minus 1 over mu. Because then by just conservation of entropy, the correct fraction will be close to 0 and the correct fraction will be close to 1. So the whole game really becomes showing that the fraction of channels which are really close to the boundaries is really very good. So it's within a polynomial factor of 1 minus this polynomial factor. So you have to basically show that this polarization happens at this fast polynomial rate. Okay. So, and how might you show that? So basically you just have to worry about showing the entropy goes to close to 0 or 1. So to track that, it's convenient to just take the product of the entropy and 1 minus h. So you just have to prove that for most i's, this quantity goes down to 0, goes to 0. And so how are we going to show that? To show, for example, that what we desire, that most of them are very close to this. And in particular, if you want to show that mu is 2 plus alpha, so the fraction which is not too close to the boundary is at most almost 1 over root n. So we're going to track this potential function which h times 1 minus h raised to the alpha. And we're going to simply prove that the average value of this is small. So you really should think of this as some sort of a moment method, because this h times 1 minus h is a quantity less than 1. So by taking its alphath power for tiny alpha, it's like a high moment. So we're basically applying the moment method for this potential function to prove that it really goes down to the boundaries fast enough. Okay. And this is the approach which was used by Fazeli and others, and we also follow that. Okay. So again,
how does this depend on the kernel used?
Okay. So we'll come to that in a second. This is exactly this slide. So far I only talked about the global process, and we want to prove this moment bound for G alpha for the average channel, a random channel at the depth D. So to do this, we will simply follow the local evolution. So we will prove this at each step. So at each step, what happens? You have some intermediate channel W prime somewhere sitting inside the tree. You apply this transformation, then that splits into L kinds of channels, W prime 1 to W prime L. And to prove the inequality written at the top, it suffices to prove that at each step, the average value of G alpha for these L children goes down by a factor of about 1 over root n. So if we do this by just applying this inductively, we get the desired result. So the kernel is going to come in exactly to ensure this property, that the polarization happens at a rate of, like at a geometric rate of 1 over root n. Okay, so that's what we want. So the kernel we need is something which, give me any channel W prime, I should find a kernel which has this property. Okay, and how are we going to do that? And this is where the earlier question will also come up. Why does it become easier for larger L? So because for larger L, we can expect what is called a sharp transition in channel entropy. So we are going to try to show the following property, that the initial number of bits, L times h of W prime minus like square root L, these channels will be extremely noisy. So their entropies will be almost close to 1, which then implies that G alpha is close to 0. And the channels at the end, these will be almost noiseless. So they'll have entropy almost close to 0. and therefore G alpha is also close to 0. Okay, and intuitively you might expect this because the later bits have all the previous bits given to them. So their entropy should be lower, and essentially we can expect this kind of transition behavior, and there will be only about root L channels and square root L channels in the middle where you have no bounds on the entropy. So G alpha is at most 1, and that exactly gives you this L to the minus half factor. Okay, so this is what we are going to shoot for. So we're going to try to get this sharp transition, and such transition behavior naturally only happens when you make L itself grow. So we can leverage that fact.
There's a question,
So
does it matter that the potential is exactly the form h times 1 minus h, or will it work for any reasonable function that's 0 at h equals 0 and h equals 1?
No, it's just a convenient one. You could probably take max of h to the alpha and 1 minus h to the alpha or something. But some high moment analog, like this power alpha, seems important, because that's like controlling a high moment. So if you could only prove this for like alpha equals 1/2, you won't get this optimal scaling. Okay, and the fact that you make alpha smaller makes the kind of sharp transition we need has to be sufficiently sharp. Okay, so I'll try to address that also shortly. Okay, so this is the behavior. We want to prove that the channel entropies jumps down from 1 to 0 very quickly in about square root L interval. Okay, so that's the kind of sharp transition we want to show. And this was already shown for the binary erasure channel. But for the binary erasure channel, something very nice happens. So note that you need to show this not for the original channel W, but for every channel which might occur in the process. For the BEC, every intermediate channel will also be a BEC. Because either there is no misinformation in the erasure context. Either you know a bit because it's some linear combination of some known bits, or you have no idea about the bit. So it's always a BEC. And for BEC, you just have one parameter to worry about, what is the erasure probability, which is also its entropy. And then this whole process becomes more amenable to understand. And in fact, Fazeli has all showed that for a random kernel, the sharp transition occurs for all BECs, regardless of what the erasure probability is. Okay, and now we have to do the same for BMS channel. Okay, that's the only thing we have to do. The rest of the ingredients remain the same. Unfortunately, things get much more complex in the BMS case, because even if you start with, say, the simple BSC, the binary symmetric channel, at the next step, you will already have a much more complicated channel. And these intermediate channels start having humongous alphabet sizes. So it doesn't seem like they have any nice common structure which we can exploit. So in fact, we cannot prove that there's a single kernel which works for all of these. So our approach is naturally to tailor make the kernel to the channel. Okay. So again, how will this change the structure is that here I have illustrated applying 2 steps of polarization with a 3x3 kernel. So in the basic setup, you will always apply the same kernel. You will apply this kernel to these 3 bits, and then the red bits all see the same channel. So you'll bundle them up together and apply the kernel, same for the blue bits and so on. And in the tree picture, this is what you do. So W splits into 3 channels. Each of those, by virtue of the same kernel, splits into 3 channels and so on and so forth. Okay, but now if you don't have the same kernel, for every channel we see in this recursive diagram, we're going to probably use a different kernel. So every node in this tree, there will be a different kernel. But otherwise, the schematic looks the same. Okay, and we still hope to get this polarization. That's a little bit of how the construction will change. So we'll have different kernels all over the place. But the main thing we need to prove is that for any BMS channel, if you give me a random, so we will actually prove the existence of a good kernel by showing that a random kernel works. So if you take a random L by L matrix, then exactly the behavior I said will happen. The first several entries will have entropy close to 1. The last ones will have entropy close to 0, and there will be a small square root L interval in the middle. Okay, and this is enough to give us the desired kernel, but there is still one glitch we have to deal with, because we want this G alpha to go down by a factor of 1 over root L, regardless of what W prime is. So this has to happen even if W prime itself has very low entropy. So what I said, this theorem suffices if the entropy of W prime is not already close to the boundaries, but if it's already very close to the boundaries, then we just revert to using Arıkan's kernel itself sufficiently tensor up. Okay, so that's one small twist we need. We'll just throw it out there. Okay, so now comes the main part of how do we prove this particular theorem. So to prove this theorem, we have to understand this quantity h of Wi. So what is h of Wi? In the Wi, you assume that you know the first I minus 1 bits of the transformation. So that really means that whatever effect the first I minus 1 rows of the kernel K had, you can remove it, because you know how they are being linearly combined. So the actual process then becomes you drop those columns. So you only have the last k columns, little k columns, and call that matrix G. And then the process simply becomes I take a random, so the previous I minus 1 things are known. So I just take the last k bits, which are random, transform it according to G, and I get these L bits, which are then affected by the channel. And if I want to predict the ith bit based on the previous thing, that simply becomes predicting the first bit of this message. Okay, so this is a little claim you can prove that this is really what is happening. So what's really happening is that
sorry, there's a question asking, can you build the explicit L by L matrix?
No, so we can only prove it exists, and then we have to find it by just searching for it. Okay, so there will be some exponential dependence on L there. So, okay. All right, so now so this is what we need to understand. So we have you're transforming a k-bit message by a code, and what is the uncertainty in the first bit given all the channel outputs? So it's basically the coding setup, but you're only trying to figure out what the first bit of the message. And if we have a random kernel k, this matrix G is also going to be random. So we just have to understand how do random linear codes fare in this metric of figuring out the first bit. And for that, we basically, that's what one can show, is that if you use a random code and the k over L is less than the capacity by about square root L factor, 1 over square root L factor, then you can predict the first bit very, very well. And this actually follows from Shannon's theorem, because if your rate is sufficiently below capacity, you can predict the entire message V very well. In particular, you can predict the first bit. The other part we need to show is that if your k over L is sufficiently bigger than the capacity, which means you're still at the top few bits in our kernel picture, then the entropy of the first bit is very close to 1. So it's almost unpredictable. Okay. And this is actually the key technical ingredient we need to prove. Okay. So the main thing we prove is a strong converse for the bit decoding of random linear codes. So we say that give me any BMS channel. If I try to use a random linear code with rate more than the capacity by about square root L, and then I send a random message through it and the channel acts on it, then it becomes very hard for me to predict even the first bit of the message. So it's a very strong converse, which shows extreme unpredictability of even the first message bit at rates above capacity. And both of these aspects are crucial for our result, that the unpredictability has to be very close to 1, the entropy, and also this has to apply at rates just 1 over root L above capacity. And one other point is that this only applies to random linear codes, because if all you care about is the first bit of the message, and you can do whatever you want, you can repeat that message 10 times and you will get better reliability. So this is something which only holds for random linear codes, but that is enough for us. Okay, so is it okay if I take 5 more minutes?
Yeah, sure, go ahead.
Okay, so I'll just spend the next slide on a proof idea of this, and then we will wrap up. Okay, so again, even if a lot of the polarization things and stuff was not clear, hopefully this part is something people can appreciate. It's just that if you try to communicate at rates above capacity, then the first bit is going to be extremely unpredictable. Okay, so how are we going to do that? So you don't really have to read these equations. All I've written here is that the average value of this uncertainty, you can just write it down using law of total probability, nothing interesting here. But the first step in our proof is to use the symmetry of the channel and linearity of the codes to say that if I look at this distribution of Y, in general, the distribution of the output depends on the input as well as this matrix G, which transforms the input. But because of the symmetry of the channel, you can pretend that it was the all zero code word which was sent, all zero message which was sent, which means the channel output doesn't really depend on G at all, because 0 is always transformed to 0. Okay, so because of this, this first probability can be written conditioned on the input being 0, and that is nice because then that is independent of G, and so the matrix G only figures in this entropy. Okay, so that's the first step. So and now, so we have this thing, and because of this, we can pretend that we have a fixed channel output Y, and because it is the output when the all zeros bit was sent, and you have about p fraction of flips. Oh, but I should have also said that I'm only proving this for the BSC with crossover probability p. So the other cases are more general. So even that illustrates the main idea. So this Y will have about p fraction of 1. So you can really fix that Y. and then try to understand this, the second term. So what is that second term? Well, it's the entropy of a bit. V1 is just a bit. So the entropy of a bit is simply the binary entropy function of its bias. So what is its bias? It's the probability of V1 given 0 equals 0 given the output, which you write it down as this ratio of these two probabilities. And what are these two probabilities? The denominator is the chance that you receive Y when you communicate using the full code G. And the numerator is the probability that you receive Y when you communicate with the code G with the first row dropped. So why is that? Because you've really set the first bit of the message to be 0, which means you don't transform according to the first row. So essentially, this is the ratio of receiving Y under two different codes, one of which is has one less row than the other. And that's going, and what do we want to prove? We want to prove that this ratio of these probabilities is very close to half, because then the entropy function will be close to 1. And this is where, in this picture, I try to illustrate this. This is the origin, and this is where Y is sitting. It has about p fraction of ones. Now, because you are at rates above capacity, sufficiently above capacity, there will be lots of code words. So this Y is actually much more likely to arise from a non-zero code word than a zero code. If you were at rates below capacity, when you got Y, you will be almost sure that you will get to 0. But now you're sufficiently above capacity. So knowing Y, you really, even if 0 was sent, you will most likely make a mistake because there'll be many non-zero codes. So most of these probabilities arise from the choice of non-zero code words. And now the punchline is that the fraction of non-zero code words in this truncated matrix G tilde at distance PL is roughly about half of that of G. Just because this has one less dimension, it's going to have about half the number of code words in the blue region in expectation. And by Chebyshev and concentration bounds, it will also have about half the code words with high probability. So with very high probability, this ratio will always be close to half, and therefore this entropy function will be close to 1. Okay, so that's really just a bird's eye view of the proof, just to at least illustrate where things like being above capacity comes in. Okay. Okay, so again, this ratio is almost half, and therefore the entropy is very close to it. Okay, and this is for the BSC. If you want to do it for the general channels, you use the fact that that's just a convex combination of BSCs. The spirit remains the same, but the calculations become a lot more technical. Okay, so that's basically it for the analysis. If you want to get a construction, there are some challenges we need to overcome. One of the primary things is that I said, you give me a channel and I'll give you a kernel. But the point is these channels get much more complicated. So, more and more complex. So they have huge alphabet size. So you cannot even give me the kernel. So what you have to actually always do is have an approximate version of these, or a quantization of these channels to polynomial alphabet size and work with them. And you have to prove that that doesn't cause any damage to your guarantees. You have to prove that even though you work with approximate versions, the actual kernels you produce will work just as well, even when the actual channels figure in the decoding. And this process, basically the way we do this, limits the decoding error probability to inverse polynomial, and improving that would be very nice. So again, that's the summary. So we have codes converging to capacity at a near quadratic rate in the block length for an arbitrary BMS channel. And so for doing this, we extended the polarization framework in a few ways. One is we said you can use larger kernels, and which was done in many works before. But we also said we don't know what kernel to use universally. So we had different kernels matched to the different channels. And to prove that these kernels exist, we had to prove a strong converse theorem for communicating at rates above capacity using random linear codes. Okay. So natural questions. So we did this for binary codes. What happens for non-binary codes? And also, can you get the decoding error probability down further? And both of these were achieved in recent work by Wang and Guruswami. One aspect they did not address is how do you actually construct the codes. But with respect to the decoding error probability and general alphabets, they achieve it. And in some work in progress, we are addressing this drawback of our thing of the decoding error probability not being only inverse polynomial. So the hope is that we can use the fact that in a lot of stages, we actually use the original Arıkan kernels to avoid the search for these kernels and get this result. So that's still work in progress. And in terms of future, it'll be nice to have a single kernel work for all these steps. We don't know how to achieve that. And as I acknowledge, the constants are horrendous, and it will be really nice to improve the constants as you tend to the optimal scaling exponent. And one last point, which I think is very interesting, which is already asked by someone, is we said that the correct fraction of channels are good, but we don't have any nice idea of which channels are good. And this can be addressed in construction by just simulating the channels and finding them. But having some analytic understanding of this would be very useful. For instance, this could shed light on if you can use polarization ideas to prove, for example, that Reed-Muller codes achieve capacity. Okay, so I think that's it, and I'll take any further questions.
Awesome, thanks a lot, Venkat. Yeah, we have time for questions now. I'm going to see if I can allow people to unmute themselves so that people can ask them themselves. I think it should be possible to unmute yourself now. You can give it a shot if you want.
Can I ask a question?
Yeah, go for it.
Hey, Venkat. I wasn't sure, did we use a single kernel throughout the construction at the end? Did we use 2 different kernels or just many different kernels? You're muted, Venkat.
Oh yeah, sorry, I muted everyone, including to unmute people. Sorry, to allow people to unmute themselves, I muted everyone. So, yeah.
I'm unmuted. Okay, Madhu, yeah, so there are as many kernels as basically nodes in the tree.
Oh, I see.
So for every channel, we have a kernel.
And so
except in places where the entropy already is small, we just use the Arıkan kernel. So those places use the same kernel.
Okay, but it's just really a host of different kernels.
Host of different kernels.
Okay.
Hi, I also have a question. This is Arman. Do you think we can achieve the precise scaling exponent of mu equal to 2 if we choose the kernel size to be slightly larger than constant?
Yeah. So yeah, the question is, yeah, I actually wondered about this too. So the question again, to repeat, was, can you achieve scaling exponent even like maybe 2 plus little o of 1 by picking L to be super constant, even bigger? I guess probably you can get something very weak by just inspecting these things, but it'll be pretty bad because L is exponential in 1 over alpha, and there are things running exponential time in L. A different approach may be to track some potential function which is not a polynomial but something else, like happens in usual Chernoff bounds. But yeah, that could be an interesting thing to investigate.
Thank you.
All right, are there other questions? Feel free to unmute yourself.
Hi, Venkat.
Hi.
I have a question. This is Elena. So what do you expect to be true for Reed-Muller codes and orderings?
Okay. So yeah, for Reed-Muller codes, you can just do the Reed-Muller ordering itself, and actually that is known to polarize. So again, so for the basic Arıkan code, you just have this G2 tensored n times, and the Reed-Muller code is just obtained by the Reed-Muller ordering is just a different ordering of these rows, and that is also known to polarize by a nice paper of Abe and Minier. But the issue is they don't know which channels are good. So if they can prove that the good channels are exactly those which are at the top in that ordering, or I guess in the bottom in that ordering, then you would prove that Reed-Muller codes achieve capacity. And I think that is likely to be true, though we don't know how to prove it. So.
But actually, I know that the Reed-Muller codes does not polarize, right? Because I can show that there is at least one bit channel which is bad. And then this is enough to show that they're not polarizing. Is it true?
So I don't know.
I think it's already in the paper of Arıkan even.
I see. So I'm not quite sure in the sense that because also note that there is this converse. I said if you believe Reed-Muller codes achieve capacity, then they have to polarize. There is no other. So this thing I said in the beginning, I didn't formally prove it. I said polarization matrices are necessary for this. You can make it formal. So if Reed-Muller codes achieve capacity, then they have to polarize. Now, yeah. So of course they may not do so with the optimal scaling exponent and other things, but
the thing is, isn't polarizing already so mean that so under this successive cancellation decoding they should achieve capacity? Is that correct?
So if they polarize, then under successive cancellation, they should achieve capacity. But note that the successive cancellation thing probably will not have an efficient implementation for the Reed-Muller ordering. So even if you prove the polarization happens, you may not get an efficient decoding algorithm because this SC decoder, the step of predicting UI given the previous bits, may not have an efficient implementation.
Okay, what you're saying is you should change maybe the ordering of the decoder. It's still successive cancellation decoder, but the ordering might be different than the one that you do for polar codes.
Yeah, or in fact, maybe no such ST style decoder even works, right? It is possible it just achieves capacity, but only under ML decoding or something. So there may not be an efficient algorithm.
Okay, I see.
Even that is not known. Yeah.
Any other questions? Arman comments that RM codes can polarize if bit channels are decoded in a different order. A new paper on this topic was published by Ye and Abe.
Yeah, so yeah, I think that's the paper I was referring to.
Mm-hmm.
Yeah.
I have a question.
So they do polarize in that order, but yeah, we don't know which channels are good. Sorry, go ahead.
So I have a question. Is there any strongly explicit algorithm to know what the good channels are? Or is it like, so like something which runs in polylog n time? I give you a channel, is it good or bad?
No, but in a certain sense, yes, because as I said, if you do the naive approach of just sampling to figure out the good channels, you can only approximate the entropies to within polynomial error factors. But in reality, you can actually find those channels which have entropy, which are inverse polynomially small. But you can do that in polynomial time. In a soft, I guess I'll give a soft yes to that thing. So in some,
So given a channel in polylog n time, you can tell whether
no, I'm not quite saying that, but I'm just saying that you can tell if the entropy is really small, like say 1/2 to the root n, but you can still do that in like poly n time.
Okay.
And if you just did that by sampling, you wouldn't be able to do that.
Mm-hmm.
Just because your accuracy has to be inverse polynomial and you won't be able to do that.
Mm-hmm.
And yeah, but so that's only known for the Arıkan code. So, yeah.
Going back to the Reed-Muller question, so Ye and Abe showed that you have this Arıkan kernel tensor product matrix, and if you go by the Reed-Muller ordering, which is the lightest to the heaviest weight vector by Hamming weight, then that polarizes.
Yes.
But that is not necessarily the Reed-Muller code, right, itself.
That's right. Yeah. So they shared it polarizes, but they did not say which indices have entropy close to 0 and which ones have close to 1. So if it is true that in that ordering, all the bottom so many things have entropy close to 0, then you'll be done. Or if all the entries are, the entropies, if it's like a step function, all the initial entropies are 1, then some bad thing happens and then it goes to 0, then you'll be done. But that they don't show.
Oh, I see. Okay.
Venkat, I have one question. This is Ihan. So,
hi.
So do you know the results by Polyansky and Makur? They have results on domination of BMS channels. So in some sense, if you fix the probability of error, then PSA is sort of the worst case channels in the sense that it's the most degraded channel. It dominates everything else. And VEC is the least degraded channel. So in some sense, the previous work did the easiest case. That's for BEC, and you did all of the cases. But I guess by Polyansky and Makur, if you can do BSC, then in principle, you should do it for every other channels. So is there a similar phenomenon in your work reflecting that fact that BSC is the worst case?
So I think it's, I'm not very sure about this, but we looked into some of this because for the strong channel Shannon theorems, in some sense, BSC is the worst. But this kind of came up for us if we could note that even if we start with the BSC, the intermediate channels are no longer BSC. So we have to deal with other channels. We did wonder whether proving this strong converse is actually the hardest only for BSC, and in which case we'll be done after we proved it for BSC. But that did not seem to be the case. So you have to prove it for each channel.
Oh,
now the forward noisy coding theorem itself, I think the BSC might be the hardest, but don't quote me on that.
I see. Okay, thanks.
And maybe one last question. So if we have time.
Yeah, go for it.
So for this like strong converse for the first bit, so you were using, I think, the linearity of the code, right? Is it correct?
Yes, yeah, linearity of the code,
And if you assume that you're not using any linear code, let's say you have a non-linear mapping of the kernel. Can you also do something similar, or I mean, just curiosity? So I.
Yeah, no, I haven't thought about that at all. So yeah, we do use the fact that it's a linear thing. We also use this, so we use the linearity heavily in the current. So.
Okay, I see. Thank you.
All right, anyone else? Oh, Alexon has another question. Oops, sorry to ask about kernel in different places again, but to clarify, when you say find a kernel K for each channel, the idea of the paper is that you choose between one of two choices. One, you either choose a completely random K when entropy of the channel is not close to 0, 1, or two, use the Arıkan kernel instead.
Yes, yeah. So if the entropy is close to the boundary, we will just do the Arıkan kernel. Otherwise, we will, by this theorem, a good kernel must exist, and then we will just find it by just going over, let's say, all kernels. So it's not, it's not a very satisfactorily explicit construction for each local level.
All right, anyone else have questions? All right, I'll take us offline in a sec. People can still hang out if they have any questions, if they want to ask Venkat if he has time. I just want to remind you that next week we have Ramon van Handel, who's going to be giving a talk on a more mathematical, let me just look up the result. It's going to be on Rademacher type and N-flow type coincide. So if you're interested in that, then be sure to join us and check it out. But if not, thanks for joining today.